Okay. Hi everyone. So this is a continuation of question 6 that we discussed for about half an hour. This is a continuation. It's the same graph and you are given the same info, which is angular velocity equals to 2.0 radian per second. Now you are asked to sketch and label the graph of velocity against time and acceleration against time for the oscillator. So the graph that you need to draw will be this velocity time graph and acceleration time graph. Okay, so we have constructed the equation in the previous video for this displacement time graph up here. We've constructed it to be x equals to 0.03 sine 2.0 t. Then after differentiating it, we obtain the equation for velocity, which is v equals to 0.06 cos 2.0 t. And after differentiating the velocity equation again, we get acceleration equation. A equals to negative 0.12 sine 2.0 t. So what you need to do is to sketch the graph for velocity and acceleration. So let me leave you for a while to try and figure this out, then I'll come back and solve the question. Okay, so I've already drawn the displacement time graph. So it's exactly what you see in the question, just that I draw it for a single oscillation only. So this represents one complete oscillation. So if we are drawing something, we are sketching a graph, it's important for us to label two things. Okay, the first thing to label would be the amplitude. Amplitude work both ways, so I think it's appropriate for us to label for both sides of the displacement. So this is 3 cm. If you want to write it in meter right now, then it will be 0.03. Then the negative side will be negative 0.03. The next thing to label will be the time needed for one complete oscillation. Okay, we call this the period. So we need to label this point here. So what is the period for this oscillation? If you are unsure, see that we have an angular velocity here. We can know that the angular velocity, the period, and the frequency are all different representation of the same thing. So what we can do is use this expression, move it around, substitution, and there you have it. The time will be pi second. So I can label here pi. This is important. If you want to fill in the middle gap, it's okay as well. You can write this as pi over 2. That's fine. Okay, so that's how you complete a displacement time graph. So let's move on and draw the velocity time graph then. Okay, the velocity time graph, it's a cosine graph and it's positive. So we can draw the shape to be something like this probably. Okay. Going up, coming back up. Okay, so this will be a cosine graph and this is one complete oscillation. You go from the maximum upward displacement, go to the maximum downward displacement, then come back up to the maximum upward displacement. One complete oscillation. Again, don't forget to label the important stuff. The first thing would be what's the value here? The value here should be 0.06. We label it for the bottom as well. negative 0.06. Okay, so this value that we've labeled here is actually okay, how should I draw it? This value here represents the maximum velocity that an object that this SHM can achieve. This is the Vmax, whereas this bottom here represent also the maximum velocity but in the negative direction. So this will represent the Vmax for positive, whereas this will represent the Vmax for negative. So what is this Vmax? We usually say Vmax is equals to plus minus A omega, right? So how does this equation comes to place? Actually, you can derive it also. You know that the general formula for displacement is A sine omega t. So if you do a bit of differentiation to find the velocity, what will come out is A omega cos omega t. Okay, this will be the differentiation of the equation of motion. So if you see here, this represents a cosine graph. That's why our graph looks like a cosine graph. It is exactly a cosine graph. It's not looking like it is a cosine graph. Okay, so if this is a cosine graph, then this value here represents the maximum, because your cosine here can only be in between -1 and 1. So you need to fluctuate within this range where the maximum is A times omega. That's why your Vmax is plus minus A omega. That's the idea behind how this equation comes into place. So now let's move on. Oh, we haven't finished label everything yet. We still have the period table. This will be pi. And since there is pi, you have pi over 2 here. Okay, so next thing is the acceleration against time graph. Acceleration against time graph, as you can see here, it has a negative sign, so be careful about it. So it's in the shape of a sine graph, but it's negative. So if it's negative, it probably looks something like this. Okay, so this is how a negative sine graph looks like. Okay, so we should label the important stuff as well. First thing to label would be the peak. I'm not drawing the horizontal line very well today, but you get what I mean. So it's 0.12 and it's negative 0.12. Then the period will be again pi and pi over 2. Okay, so if we do a bit of the same explanation like just now, this line here represents the maximum acceleration that this SHM can achieve. We call this the A max in the positive sign. This line here represents also maximum acceleration, but in negative. So because your acceleration will be fluctuating within this range, your A max, your maximum acceleration, will be plus minus A omega square. If you're not sure how this thing comes into place, again, A is dv over dt. So if you differentiate this equation up here, bring this equation, the whole equation, you bring it down, and you differentiate it, what will come out is cos. If you differentiate it, become negative sine. So it's negative A omega square sine omega t. You can see here that it's also a sine graph. That's why you're drawing a sine graph, but you have a negative sign in front. That's why the shape is negative sine. You know that this sign will have a range of negative 1 to 1. It doesn't equal, you can hit 1. Okay, so this will be our maximum. And that's why you get this. Okay, so that's how you derive the maximum acceleration. It's plus minus a omega square. Plus minus because you're fluctuating within the range of negative 0.12 to positive 0.12. So that's maximum acceleration. Okay, so we have finished drawing this graph, but I would like to discuss a bit more about sketching graph for chapter 9. Okay, one thing is, in our syllabus, we are asked to teach you that the general formula for equation of motion is a sine omega t. But actually, this is not really general. Okay, so this is not a formula you can just main pakai saja. This is not the most general formula. There are a lot of different equation of motion that doesn't look like this. Let's say you can have a cosine omega t. This is also an equation of motion. You can have x equals to, say, negative a sine omega t, also an option. X can be equals to negative a cosine omega t. That is also a valid SHM equation. And also you can have even more general forms like a sine. Okay, this is probably out of your syllabus, but it was in your syllabus last time, so I'll just talk about it here. You can add on this angle behind here that we call phase angle or phase constant. Okay, so it might be difficult for me to explain why it's phase constant. Probably let's just move on to look at some graph. Maybe that will help you better. Okay, let's move downward a little bit. Okay, so this is a bit complicated, but bear with me. So just now I have said that this is the formula that we learned for our syllabus, but you can have different ways of doing SHM as well. Okay, let me elaborate what does it mean by different ways of doing SHM. If you are in the first case here, what happens is your object starts at the equilibrium position. So it starts at the equilibrium position. But it's not necessary to really start from the equilibrium position. You can start from a maximum displacement, like you compress a spring first, then when time starts, you let go. Then the spring starts to oscillate back to the equilibrium position, then starts oscillating. In this case, it doesn't start with the equilibrium position. That is second case. Then you have third case. Third case can be not oscillating upward first. It can oscillate downward first. Okay, it's flexible. If you push the mass to the left hand side before letting it springs back to the right hand side, yeah, that's a negative sine graph. So there are many ways to cause an SHM to happen. You can start from an equilibrium, you can start from the amplitude, many different ways. Like this one, the case number 4, you can start at the negative maximum displacement, then you move back towards the equilibrium position. That's case number 4. And case number 5. Case number 5 is even more what do you call it? More general. Equation 5 basically means you can start from anywhere, not the amplitude, not the equilibrium position, but somewhere in between the amplitude and the equilibrium position. It's like you half compress the spring but not fully compress it. Then when you want to release, you press it to the spring. It's a bit difficult to explain, but basically it just doesn't start from the equilibrium, it doesn't start from the amplitude, it starts somewhere in the middle. That's why the graph should actually, for full complete oscillation starting from equilibrium, it should look like this. But no, it starts from somewhere in the middle, not the amplitude, not the equilibrium position, somewhere in the middle. Okay, this middle, how to get this middle? It comes from this phase constant here. Okay, it's out in our syllabus, but that's what the phase constant means. This is a constant, means by it's a constant introduced because you are not starting in the amplitude, you are not starting at the equilibrium position, you are starting somewhere in the middle. That's why you have a phase constant. It's because you start differently. Okay, let's not dive too deep about it, but if you go and differentiate all of these equations and you plot their velocity time graph, they all looks a bit differently, but they are all sinusoidal graphs. And if you go further and differentiate the velocity equations, you get the acceleration equation, and you plot it, then it'll be a sinusoidal graph as well. One thing to be careful is, even though they are all sinusoidal graph, but what are you labeling for the amplitude for each graph is different. You see here, for this you are labeling it as A and negative A. But for velocity time graph, because what you differentiate is, it will start with A omega. So it means by what you are labeling here is actually A omega and negative A omega. For acceleration, what you are plotting, there will be negative A omega square or positive A omega square. So it will be fluctuating around this value. So your axis, your data should be A omega square and negative A omega square. So be careful with what you are labeling for the amplitude of the graph. Okay, the amplitude of the graph can be A for displacement time graph, it can be A omega for velocity time graph, it can be A omega square for acceleration time graph. So just be careful when you're plotting something. Okay, so a quick tips for graph plotting. Actually, if you notice the shape here, the xt graph, the vt graph, and the at graph are just shifting a little bit. What do I mean here is, if you are being lazy or you want to double check your answer, the velocity time graph should actually look just something like this. You can plot here to be velocity time graph. Then that is your velocity time graph. Your velocity time graph will look exactly like this. Okay, so you neglect this portion. So this portion, this let me put it in the color then. This purple portion will be what you are plotting for your velocity time graph, just like what we plot here. Okay, cool. So if you want to get the acceleration time graph, we move the axis further. And there you have it, acceleration time graph. Okay, so if you want to figure out the shape, you can just move the axis by 1/4 of a complete oscillation. So it's a bit difficult to explain. This is part 1, this is part 2 of an complete oscillation, this is part 3, This is part 4. So you move it by 1/4 of a complete acceleration, you get the shape of a velocity time graph. If you move another 1/4 of a complete oscillation, you get the shape of an acceleration time graph. What you need to be careful is just labeling things correctly. For the velocity time graph, it will be 6 cm per second and negative 6 cm per second. For the acceleration time graph, it should be 12 cm per second squared and negative 12 cm per second squared. Okay, so you can just extend this line further if you are running out of sinusoidal curve. Okay, so that's a quick way of figuring out the shape of the velocity time graph and acceleration time graph. But to be proper, what you should do is to get these equations and plot it according to the equation. Okay, so that's it for graph plotting in chapter 9, simple harmonic motion. Thank you very much.